I expect that we're going to get a spread of opinions. Yep, we do. So let's think about it. The fact that light rays travel in a straight line, well, if light is particles, it's pretty easy to imagine that they just go straight, right? And likewise, for D, that solid objects cast defined shadows. Well, if light is a bunch of particles, if the particles hit something, they stop, and if they don't hit it, they go past, and that's where the shadow comes from. So that's not so hard to understand with the corpuscle theory. What about B? The angle of incidence from a flat mirror equals the angle of reflection. Well, imagine a ball bouncing off a wall, right? That's exactly what you get. If light is corpuscles, they just bounce off the mirror. Now, some things act like mirrors and some things don't. That's a little harder to explain. Now, C and E are kind of related to each other, right? We know, of course. Light rays are bent. The fact that light rays are bent or refracted upon entering a solid medium, that we can explain with waves pretty easily, right? And it's a little bit harder. Why would blue particles be bent more by a prism than red particles? Not clear. Nevertheless, Newton stuck to his guns. And that the fact that white light can be separated at all into a spectrum of colors with a prism, I think that is probably really hard to explain with either theory, right? Either waves or corpuscles. I'm not sure there's a perfect answer here. But I think I agree with you guys that C and E are the best answers here. But it makes you think. There's no one right answer. Now, measuring the speed of light is absolutely fascinating, and having done so really led to a great revolution in physics. It was Galileo in around 1610 or so who got his friends together to climb up to nearby mountain peaks near Pisa, with lanterns at night. And the idea was Galileo would open his lantern, and then when the next person saw it, they would open their lantern, and then on another peak, when they saw the second one, then they opened their lantern, and then when Galileo sees it, he's sitting there counting 1 Galileo, 2 Galileo. And when he counts how long it takes for that light to travel in that triangle. Well, you can imagine what happened with this experiment. Probably had a good time, but they couldn't detect any finite speed for light. So it's really, really, really fast was what they decided. Then a couple things happened. In 1656, Christian Huygens, the same one who we were just talking about with the wave nature of light, he invented the pendulum clock. And that was an enormous advance for science. Why? Because with a pendulum clock, we could measure time intervals. Before the pendulum clock, we had an accuracy of maybe 20 minutes or something like 15 or 20 minutes. After the pendulum clock, we could measure time intervals to 10, 15 seconds accuracy over periods of days. And so 20 years later, Ole Romer, an astronomer, decided he would make as good measurements as he could using this newfangled pendulum clock that he had of the orbital periods of the moons of Jupiter, which of course Galileo had discovered with his telescope early in the century. The innermost moon has a period of about 1.3 days, orbital period, and so you can look for eclipses of it. We see it in its orbital plane, so you can see when it winks out going across the face of Jupiter. And we call that an eclipse of Io. And so he kept track of those over periods of years and noticed something. He noticed that some times of year, the eclipses seemed to come a little bit early, and other times of the year, they came late. And then he realized that it wasn't the year so much as whether or not the Earth was going toward Jupiter or going away from Jupiter. Because when it was far away, it would take the light longer to reach the Earth when it was on the far side of the sun, if you will, from Jupiter. But 6 months later, when the Earth went around and it was on the Jupiter side of the sun, there was less time. It took the light less coming from the Jupiter's moon. It took it less time to reach the Earth. Didn't have to traverse all that additional distance corresponding to the size of the Earth's orbit. And two genius things. First of all, to think of doing it to begin with, keep good records, do precise measurements. And secondly, to interpret it correctly as meaning that light had a finite speed. He didn't get a perfect answer, 2 times 10 to the 8th meters per second. Well, of course, he didn't use meters then, whatever they used, furlongs per fortnight or whatever. But you know, we know the true value is 3, so that's not so bad. Another astronomer in the early 1700s, Bradley, discovered another effect, which was called stellar aberration. Now think of the plane of the Earth's orbit as it's going around, and you're going to look at a star that is, let's say, 90 degrees to the plane of the orbit. The light is coming straight down onto the Earth, but the Earth is moving like that at basically 90 degrees to the light coming in. Well, you know what happens when you're outside. If the rain is falling straight down, but you're in a car, the rain appears to be tilted by a certain amount. It has an apparent angle that it's hitting your car at, right? Well, same with light. And because of the motion of the Earth through space, which is around 30,000 kilometers per second, 30,000 meters per second, not kilometers, 30,000 meters per second, 30 kilometers per second, and that was known at that time, he was able to see a tiny shift in the apparent position of stars. And then 6 months later, it was shifted in the opposite direction. Totally bizarre, right? He didn't see any shift for stars toward which the Earth was moving or away from which the Earth was moving in the plane of the Earth's orbit. And from this stellar aberration, you got a fantastically precise, at least for the time, value for the speed of light, 3.01, 10 to the 8th meters per second. Well, in the 19th century, people started doing this mechanically. Fizeau, a French physicist, came up with a method where, imagine you have a toothed wheel, and you have a beam of light, and when there's a gap, the beam can pass through, and then it closes off again. So you have a chopped beam, if you will. And you place several of these toothed wheels together, you spin them really fast, but as you go along this axle, you rotate each one by a little bit so that only light going at the speed of light can make it through. So you set the rotation of this axle just so that these pulses can make it through the tooths, the gaps between the teeth in these wheels. He got a pretty good value, 3.15, 10 to the 8th meters per second. The techniques were refined, and a new technique involving rotating mirrors was invented by Foucault. He got a very close value with an error that he estimated to be 500 out of 298,000. Michelson, then, who is famous for having done the Michelson-Morley experiment, if you've ever heard of that, which showed that the speed of light is the same in all directions and relative to any observer, he got 10 times better result with, again, a rotating mirror experiment, performed, I believe, in Cleveland. And then, as you'll see in a minute, you can take just electromagnetic theory and the constants, the magnetic and electric constants, and combine them to get the speed of light. And so just by doing precise measurements of electrical forces and magnetic field forces, they were able to get it down to 30. 1926, oh, look who came back. Started first in 1879. He kept doing the same experiment, I guess, until 1926. That's true dedication to physics. Again, with rotating mirrors, he got 10 times better result than he did the first time, which is pretty good. But wasn't really improved upon until the microwave cavities in 1947, then measurement using radio in 1958. Very, very precise. And then people began to realize that this was kind of a futile exercise. Why? Why do we need to measure the speed of light with such accuracy? We can just define it. We can base our definition of not only the meter, but the second on the speed of light. And so in 1983, by international convention, the Système International of units was established, so what we call the MKS system, 1983. And we've defined now the speed of light to be 299,792,458 meters per second, about 30 centimeters in 1 nanosecond. And we base this on cesium-133. If we say 1 second is 9.192 billion cycles of radiation from cesium-133. And indeed, what we call atomic clocks, and the world's official atomic clocks are in the UK, in the Greenwich Observatory, and in the United States Naval Observatory in Washington, D.C. There's a bank of 4 of these cesium clocks. So you have cesium-133, a particular isotope of cesium, inside these tubes, and you excite it and actually look at the light coming off it and actually count the wave crests arriving. And if you count this many, that's 1 second, and you tick off a second on your clock. Literally, that's how it's done. This is how the Time Lords actually work, and they live in Washington and London. All our clocks, every clock in here, in your cell phone, for example, is timed to these guys at the Naval Observatory in London. It's sent out to the GPS satellites and everything else. Now, so that's how we define a second. We define a meter to be the distance that radiation travels in 1 over that number of a second in a vacuum. So that's 1 meter. That's how the meter is defined. We no longer have well, there probably is still the historic meter stick in some vault in the basement in Paris, but that's only of historical interest now. We define the meter and the second, these really fundamental measurements for all of physics based on a concept. And the concept is that light coming from this kind of atom has that many cycles per second. We just defined it, okay? And we defined it so as to agree with the previous definitions of what we meant by a meter. You know where a meter came from, by the way? It was invented around the time of the French Revolution. They changed from whatever length they were using before to 1/10,000,000th of the distance from the North Pole to the equator. So almost by definition, the Earth is 40,000 kilometers in circumference. Of course, it's different at the equator and the poles. Never mind that. So all these, it's kind of a fascinating story how we came by this system of units that we use today.